Today we're going to focus on graphing linear equations, including those with inequalities, quadratic equations. We're going to talk about transformations, graphing radical functions, cubic functions, absolute value equations, rational expressions, exponential, and even logarithmic equations. So let's begin. Let's start with the basics. Let's say if we want to graph y is equal to 2x plus 3. Now there's many ways to graph it. So the first way we're going to use is we're going to make a table. Let's keep things simple. So let's say if you have your xy table, let's plot some points. So we're going to plot the point -1, 0, and 1. We don't really need that many points. Okay, so at -1, if we plug in -1 for x, so 2 times -1 plus 3, that's -2 plus 3, that's 1. If you plug in 0, you should get 3. If you plug in 1, 2 plus 3 is 5. And then you just got to plot those points. So here's -1 on the x-axis. And over here, y is 1. That's our first point. When x is 0 and y is 3, we have this point here. I'm going to plot another point because my graph doesn't go up to 5. So I'm going to plot -2. If we plug in -2 for x, that's 2 times -2, that's -4. Plus 3, we get -1. So that -2 is around somewhere over here. And then you could just connect those points with a line. This is just a rough sketch. My graph is not that perfect, but that's the general idea of how to plot or how to graph a linear equation using a table. You just got to pick a few points and just plug it in. But now let's see if we can graph another question just like that, but without making a table. Let's say if we have y is equal to -2x plus 1. Okay, this equation is in slope-intercept form, mx plus b. b is 1, that's your y-intercept. So that's where your graph is going to start at 1. M is the slope. The slope is -2, which is the same as -2 over 1. This is your rise, and this is the run, the rise over run. So every time you move 1 unit to the right, it needs to go down 2 units. So 1 unit to the right, down 2. Our next point is over here. And if we go 1 unit to the right, down 2, here's our next point. And 1 unit to the right, down 2, it's going to be somewhere over here. And then we just got to connect those points with a line. So that's the slope-intercept method. You just plot the y-intercept and then use the slope to find each successive point. So now let's try another example just like that, but using fractions. So let's say if you have this equation, y is equal to -3/4 x plus 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4. Let's go up to 8. 5, 6, 7, 8. So the y-intercept is 5. So that's going to be the first point. Now the slope is -3 over 4. So -3 is the rise and 4 is the run. So we're going to travel 4 units to the right and we're going to go down 3 units. So our next point is over here. And then we're going to do the same thing. We're going to travel 4 units to the right towards 8 and down 3. So we're going to be down at -1. And then just connect those points with a line. So go ahead and try this example. Feel free to pause the video and give this problem a shot. And when you're ready, just unpause it. Okay, so let's begin. Let's begin by plotting the y-intercept, which is at -2. And the slope is 2 over 3. So our rise is 2 and the run is 3. We're going to go up 2 units and then over 3 units to the right. And then same thing, up 2 over 3. So we got these 3 points to plot. And then once you feel like you have enough points, you really only need at least 2 to make a good line. But once you have enough points, you could just plot it. So that's how you can graph linear equations in slope-intercept form. But now let's talk about how to graph it when it's in standard form. Standard form is ax plus by is equal to c. So let's say if we have this equation, 2x plus 3y is equal to 6. Now what you want to do is you want to find the x and y intercepts. So to find the x-intercept, plug in 0 for y. So this becomes 0. So 2x equals 6. If you divide both sides by 2, you get x equals 3. So you get the point 3 comma 0. So that's the x-intercept. To find the y-intercept, plug in 0 for x. So you get 3y is equal to 6. And if you divide both sides by 3, y is equal to 2. So your y-intercept is 0 comma 2. And that's what you want to do if you have an equation in standard form. And then once you have those two intercepts, just plot those 2 points and connect them with a line. So 1, 2, 3, 4. 1, 2, 3, 4. Okay, so the first point is at 0, 2. The next one is at 3, 0. And then just connect those 2 points with a line. That's the simplest way to graph an equation in standard form. So let's try another example. Let's say if we have 3x minus 2y is equal to 12. Go ahead and try this, and then plot it when you're ready. So let's find the x-intercept. If we plug in 0 for y, the 2y disappears. So we're just going to get 3x is equal to 12. And if we divide both sides by 4, by 3, 12 divided by 3 is 4. So we get the point 4 comma 0. And for the y-intercept, we're going to plug in 0 for x. So we're just going to get negative 2y is equal to 12. And we're going to divide both sides by negative 2. So we're going to get y is equal to negative 6. Excuse me. Which is the point 0, negative 6. So we have 0, negative 6 and 4, 0. And we're just going to connect those 2 points with a line. I don't have a ruler, so that's just, my graph won't look perfectly straight. But you get the point, though. So now you know how to plot it in standard form. How would you graph an equation that looks like this? Y is equal to 3. How would you plot that? All you got to do, if y equals a number, it's just a horizontal line at 3. That's how you graph it. And if you get a question that looks like this, let's say x is equal to 2, it's simply a vertical line at 2. So it looks like this. So that's how you can graph a linear equation if y or x equals a constant. But now let's talk about graphing inequalities. Let's say if you have this question, y is greater than 2x minus 4, and y is less than or equal to negative 3 over 2 x plus 3. By the way, if it's in standard form, make sure to convert it to slope-intercept form, which is what we see here. Keep in mind, slope-intercept form is like this. Y equals mx plus b. You want y to be on one side of the inequality. It's going to make it a lot easier to graph it. Okay, so go ahead and plot these equations in the meantime. So let's plot the first one. So the y-intercept is -4, and the slope is 2. So every time we move 1 unit to the right, we're going to go up 2. 1 unit to the right, up 2. The slope is 2 over 1. And notice that y is greater than 2x minus 4, but not greater than or equal to. If it's just greater than, we need to use a dash line. Now for this one, this is going to be a solid line because it's less than or equal to -3 over 2x plus 3. But for this one, make sure you use like a dash line. So now let's graph the other equation. So the y-intercept is at 3, and the slope is -3 over 2. That means as you move 2 units to the right, the run is 2, the rise is -3. So we need to go down 3. So over 2, down 3, and then over 2, down 3 again. And then over 2, down 3. And it's going to be a solid line. Okay, so now we need to know which region to shade. There's 4 regions in the graph. This is the first one, this is the second one, this is the third, and this is the fourth. Ignore the x and y axis. Look at the 4 regions created by the green and yellow line. When you shade it, it's going to be one of those 4 regions. So let's focus on this equation first. Y is greater than 2x minus 4. So the green line is the 2x minus 4 line. Greater than, I'm going to shade it in white, is anywhere above that line. So that entire region that's greater than the line, than the green line. Now for the yellow line, y is less than or equal to, so it's below the yellow line. I'm going to shade that in purple. So this is the region below the yellow line. Now we need to shade the region where it's true for both, and it's true in this region here. That's where we have both the purple and the white line. So this is where the answer is. On a test, this is the only region you should shade. The other ones, erase the marks that you made. And that's how you choose the right region to shade. So let's try another example. Let's say if x is greater than -3, y is less than or equal to 5, and y is greater than x minus 3. So x is at -3. That's going to be a vertical line, and it's going to be a dashed line because it's just greater than but not equal to. And y is less than 5, so that's a horizontal line at 5, but it's a solid line. And y is greater than x minus 3. So the y-intercept, the y-intercept is at -3, and there's a 1 in front of x, so the slope is 1. So every time you move 1 to the right, you go up 1. And it's going to be a dash line. Now we need to know where to shade it. So let's look at this first equation. X is greater than -3. It's greater than -3 to the right, anywhere to the right of this function. Now y is less than 5. It's less than 5 below this line, anywhere below this line. And y is also greater than x minus 3. It's greater than x minus 3 above this line. So we need to choose the region in which all arrows are located in. If you notice, it's true within this triangle. So this is the region that we shade, because all three equations are true in that region. And that's how you do it. Okay, so now let's move on to quadratic equations. So let's say if you have this graph, y is equal to x squared plus 2x plus 3. Notice that it's in standard form. Ax squared plus bx plus c. Now for this example, we're going to make a data table and we're going to plot points. So if you want to make a data table, you want to find the vertex first to make your life a lot easier. And the x-coordinate of the vertex is negative b over 2a. That's where the axis of symmetry is. So let's say if you have a graph that looks like this. This equation will get this x-coordinate. And this is useful because, let's say if you plot this point and you choose this point, they're going to have the same y value. And these 2 points will have the same y value. So if you want 5 points, you really need to find 3. And 2 of them will be the same as the other 2. So a is 1. This is a. And b is 2. So let's use the equation. X is equal to negative b, which is negative 2, over 2 times a, or 2 times 1. So the vertex is at x equals negative 1. Now we're going to pick 5 points. But our center point is going to be the vertex, negative 1. We're going to pick 2 points to the right of that point and 2 points to the left. 2 points to the left of negative 1 is negative 2 and negative 3. And 2 points to the right of it is 0 and 1. So now let's plug in these numbers in. Let's start with negative 1. If we plug in negative 1 for x, we get negative 1 squared plus 2 times negative 1 plus 3. So that's 1 minus 2 plus 3, which is 2. If we plug in, let's say 0 for x, it's just going to be 0 squared plus 2 times 0 plus 3, which is just 3. So 0 and negative 2 are going to have the same y value because they're equidistant from the vertex. Let's plug in 1. It's easier to plug in 1 than negative 3. So 1 squared plus 2 times 1 plus 3, that's going to be 6. So negative 3 also is going to have the same y value, 6. Alright, so let's make our graph. The majority of the graph is at the top. So 1, 2, 3, 4, 5, 6. And most of our x values is on the left side. So 1, 2, 3, 4. 1, 2, 3, 4. So the first point is at 0, negative 1, 2, which is here. That's the vertex. Next we have the point 0, 3, and a negative 2, 3. And then we have 1, comma 6, which is up here somewhere, and negative 3, comma 6. So now we can graph it, and it's going to look like this. I can't believe I missed this point. So that's a rough sketch. The axis of symmetry is this line right here. It's simply x equals negative 1. It's the x-coordinate of the vertex. So that's the AOS, axis of symmetry. If you need to find the minimum value is the y-coordinate of the vertex. It's right there. That's where the minimum is located. Let's try another example like this for the sake of practice. So let's say if we have y is equal to 2x squared minus 4x plus 1. So let's find the vertex first. It's negative b, which is negative 4, over 2a. A is 2. So this is A, this is B. So this is equal to 1. So let's make our table. And we need 2 points to the left of 1. That's 0 and -1. And 2 points to the right, 2 and 3. So let's begin by plugging 1 for x. So 2 times 1 squared minus 4 times 1 plus 1. So this is 2 minus 4 plus 1. And that's equal to -1. Now it's easier if we plug in 0 instead of 2. So 2 times 0 squared minus 4 times 0 plus 1 is 1. The next point we're going to plug in is -1. This is also going to be 1, by the way. So this is -1 squared is 1 times 2. -4 times -1 is 4. So we're going to get 7 for this point, which means this one is also going to be 7. Okay, so now let's make our graph. So it's going to go up to at least 7. And most of our x values will be on the right side. So our vertex is at 1, -1, which is over here. Our next point is at 0, 1. And we have another one at 2, 1. And then 3, 7, which is all the way here. And -1, 7, which is right where I put the 7. So then we can graph it. And here is the axis of symmetry. It's x equals the x-coordinate of the vertex. So that's how you can plot quadratic equations using a table. But now let's say if we don't want to make a table. Let's say if you want to graph it a simpler way. So let's say you have y is equal to x squared minus 2x plus 3. Find the vertex as usual. It's -b over 2a. So it's -2 over 2 times 1. So therefore x is 1. Now you want to find the y-coordinate at that point. So if you plug in 1 for x, you get 1 squared minus 2 times 1 plus 3. That's 4 minus 2, which is 2. So we got the point 1, 2. So our graph is initially right here. So here's what you can do. Let me show you a pattern. Let's say if you plug in 1 for x, you're going to get 1 for y, right? If you plug in 2 for x, you're going to get 4 for y. If you plug in 3 for x, you're going to get 9 for y. So once you have your vertex, and this is 1x squared, by the way, because if it was 2x squared, you have to double everything. To find the next point after you have the vertex, move 1 to the right and then up 1. And do the same thing for the left side. 1 to the left, up 1. Because 1 squared equals 1. Now, 2 squared is 4. So starting from your vertex, as you move 2 to the right, go up 4. 1, 2, 3, 4. Same thing here. 2 to the right, up 4. And that's a quick way you can plot this equation without needing a data table. So now we're going to focus on graphing these equations but in vertex form. So let's talk about how to convert a quadratic equation from standard form to vertex form. Now there's something called completing the square. So here's what you need to do. You have x squared plus 6x. We're going to focus on that number 6. Take half of that number and then square it. Half of 6 is 3. And we're going to square it. We still have the minus 3. Now notice that we added 9 to the right side. So we change the equation. To balance that, we need to add 9 to the left side or subtract 9 from the right side. Since I don't want to change the left side, I'm just going to put minus 9 on the right side. So if you add 9 and subtract 9, you haven't changed the value of the equation. Imagine if you have a bank account. Let's say you have $1,000 in your bank account. If you add 100 and take away 100, it's still the same. So the two equations are equal to each other. But this can be factored. If you factor it, here's the shortcut method. It's going to be what you see here, x, and whatever this sign is, plus whatever this number is before you square it, 3 squared. It's always going to work out that way. And then these two numbers you can combine. So now you have it in vertex form, which is x minus h squared plus k. The vertex is h comma k. So in this form, you can easily see what the vertex is. So in our example, notice that h and negative h, they have the opposite sign. So you got to switch it from 3 to negative 3. This is h. And k, the sign is the same. It's both positive. So whatever this number is, that's k. You don't change it. So it's negative 3, negative 12. I'm going to go by 2's. 2, 4, 6, 8, 10, 12. So that's negative 12. 2, 4, 6, 8, and so forth. So we have the point negative 3, negative 12, which is somewhere in this region. And since 1 squared equals 1, as you move 1 to the right, go up 1. So that's going to be somewhere over here at negative 2 / negative 11. 1 to the right, up 1. And then as you go 2 to the right, you need to go up 4. So from negative 12, it's going to be at negative 8. And then 2 to the right, up 4. Now if we go 3 to the right, 3 squared is 9. We need to go up 9. So that will take us to negative 3. And 3 to the right here, which will be at negative 6, with the y value will also be at negative 3. If we go 4 to the right, 4 squared is 16. So we'll be at, the vertex is at negative 3. So 4 to the right, x will be 1. Negative 3 plus 4 is 1. And negative 12 plus 16 is 4. So we'll be at 1 comma 4, which is somewhere over here. And if we go 4 to the left, negative 3 minus 4, that's negative 7. And the y value should still be the same. It should be around 4 as well. And now we can graph it. So that's a rough sketch. All my sketches are rough. So that's what you can do if you have it in vertex form. Let's try another example. So let's say if you have y is equal to negative x minus 3 squared plus 4. Now this negative sign tells you that the graph is going to open downward. So our vertex, change negative 3 to positive 3, but don't change the 4. That's our vertex, 3 comma 4. So let's plot that point. So here's 3 comma 4, and we're going to need more points on the right side. Now, we know the graph is going down. So as we move 1 to the right, it's going to go down 1. And 1 to the left, down 1. 2 to the right, it's going to go down 4, starting from the vertex. So it's going to be at 0 on the x-axis. 2 to the left is also going to be down 4. Now if we go 3 to the right from the vertex, which will be over here, we need to go down 9. So we should be at negative 5, which is over here. And if we go 3 to the right, will be at the y-axis, and it will be down 5 as well. So this graph looks something like this. And that's how you graph it. Now what about this one? Let's say if there's a 2 in front of the parentheses. So how does it modify our process? So the vertex, we know it's -1. You change the +1 to -1, comma -2. This is going to stay, k is going to be the same. My lines are never straight. So notice that it's +2. So that means the graph is going to open upward. So let's plot the vertex. So it's at -1, comma -2, which is over here somewhere. Now, we won't be moving 1 to the right and up 1 because our parent function is y equals 2x squared. There's a 2 in front. So if you plug in 1 for x, you're going to get 2 for y. If you plug in 2 for x, you're going to get 8 for y. So as we move 1 to the right, it's not going to go up 1. It's going to go up 2 because it's going to be times 2. So 1 to the right, up 2, that should be over here somewhere. 1 to the left, up 2, starting from the vertex. As we go 2 to the right, we need to go up 8 instead of up 4. 2 squared is 4, but we got to multiply it by 2. So if we go up 8, we should be at 6 from -2. And 2 to the left, we need to go up 8 as well. It's going to be at the same point. And so that's how you graph it. And the axis of symmetry, if you have to find it, it's x equals this value, -1. So here's the line of symmetry. It's symmetric about that line. And this graph has a minimum. Whenever you have a positive number here, the graph always has a minimum. And the minimum value is simply the y-coordinate of the vertex. It's -2. When it opens downward, let's say if you have -x squared, then you have a maximum. Because sometimes you may get like word problems where they ask you what is the maximum value of this function. Just find the vertex and look for the y value. So that's it for quadratic equations. Now let's move on to absolute value functions. The absolute value of x looks like this. It's a V shape. And it has a slope of 1. So let's say if we want to graph the absolute value of x minus 3 plus 4. First, need to find the vertex. So we need to move 3 to the right because we have a -3 on the inside, and up 4. Kind of like the last problem, the vertex is 3, 4. You change what's on the inside, but you don't change what's on the outside. Now, the slope is 1 for this problem. So as you move 1 to the right, you need to go up 1. 1 to the left, up 1. It's symmetrical, just like the quadratic function. But notice that it's y equals x rather than y equals x squared. So when x is 1, y is 1. When x is 2, y is 2. So the slope is going to be 1. And then just keep moving 1 to the right and up 1. And then just plot the graph. So that's how you can graph absolute value functions. But now let's say if we have y is equal to -2, x plus 1, minus 3. Now the fact that it's negative on the outside means that it's going to open downward instead of upward. And the fact that we see a 2, the slope is now 2 instead of 1. So as we move 1 to the right, it's going to go down 2. And it's going to the slope is constant. It's going to always be 2. So first let's plot the vertex, which is -1, -3. So it's over here somewhere, -1, -3. And we said that's going to go downward. So as we move 1 to the right, it's going to go down 2. Let me use a different color. And 1 to the left, down 2. And one more time, 1 to the right, down 2. 1 to the left, down 2. So it's going to look something like this. So that's how you can graph absolute value functions. So let's move on to cubic functions. Let's say if you have y is equal to x cubed. The parent function for this graph looks something like this. That's just a rough sketch. So let's say if you want to graph this equation. The center point, where it should be the origin, it's at 1, 2. You change the -1 but not the 2. So the shift, it moves 1 to the right and it moves up 2. What you see on the inside is the horizontal shift, which is 1 to the right. This is the vertical shift, it's up 2. So the origin is now at 1, 2. Now we can draw a rough sketch if we want. We can do something like, if we want to, but let's actually get points and make this graph more accurate. So our parent function is y equals x cubed. 1 to the third is 1. 2 to the third is 8. So to get the first 2 points, as you move 1 to the right, go up 1. 1 to the left, go down 1. And now if you move 2 to the right, you need to go up 8. And we really don't have the space for that, but it's probably going to be somewhere over here. And if we move 2 to the left, we need to go down 8. Now this we can plot, because that's somewhere, that's going to be at -6. So down 8 will be all the way over here. So now we can get a more accurate sketch. So it's going to look something like that. So let's try one more example with cubic functions. So let's say if you have y equals, instead of putting -2, I'm going to put -1/2 because I don't want to go up 16. Let's say if we have this, and it's -1. We know the center is going to be at -3, -1. So it's going to shift 3 units to the left and down 1. So it's at -3, -1, which is in this area. And let's say if we move 1 unit to the right. Oh, by the way, notice that it's negative. Positive x cubed looks like this. Negative x cubed looks like that. So we have a decrease in function rather than an increase in function. So as we move 1 to the right, this is supposed to be cubed, by the way. 1 to the third is 1, but we got a half, so we should move down a half. So 1 to the right is going to go down a half because of this number. 1 to the left is going to go up a half. Now 2 to the third is 8, but times a half is 4. So as we move 2 to the right, it's going to go down 4. So from -1 to -5. And as we move 2 to the left, this point should actually be here. Let me fix that. 1 to the left should have been up a half. 2 to the right, that's down 4. So it's over here at -5. And 2 to the left, we need to go up 4. So 1, 2, 3, 4. It should be over here somewhere. So now let's see if we can make our graph. So we have to be, the function has to be decreasing instead of increasing, only because of the negative sign. So that's a rough sketch for that graph. So now let's go over radical functions. Let's say if we have this function, the square root of x. The parent function for that looks like this. And if you have, let's say, negative square root x, the negative in front causes it to flip over the x-axis, or it's a reflection across the x-axis, so it looks like this. And let's say if you have a negative on the inside, it reflects across the y-axis, so it looks like that. And if you have a negative both on the inside and on the outside, it reflects across the origin, so it looks like this. The way I like to see this, let's say if here x is positive and y is positive, so x and y are positive in quadrant 1, so it goes towards quadrant 1. Here, x is positive, but y is negative, so that's quadrant 4. X is positive as you go to the right, but y is negative as you go down. Here, x is negative, y is positive. That's quadrant 2. And when x and y are both negative, it's quadrant 3. That's an easy technique you can use to see where the graph is going to go for a radical x. But now let's apply it in a problem. So let's start with a straightforward one. Let's say if we have y is equal to the square root of x plus 3 minus 2. So the origin, it's shifted 3 to the left and down 2. So it's going to start over here. Now the parent function is the square root of x. The square root of 1 is 1, and the square root of 4 is 2, and the square root of 9 is 3. So as we move 1 to the right, go up 1. As you move 4 to the right, go up 2. So that's going to be somewhere over here. And as you move 9 to the right from your original point, go up 3. So right now we're at negative 3. If we move 9 to the right, we should be at positive 6. And going up 3, we need to be at y equals 1. So that's our graph. It starts from here. Now one thing I should have mentioned is domain and range. What is the domain for this function? And what's the range? The domain is the x values. The range is the y values. If you want to find the domain, analyze it from left to right. So it starts at the lowest x value is at negative 3. There's nothing before that. And the highest x value, it goes to infinity. So your domain is from negative 3 to infinity, and it includes negative 3. The range is the y values. The lowest y value is at negative 2, which is that number. And this arrow, it keeps going up, but it goes up slowly and slowly. But it goes up to infinity. So the range is from negative 2 to infinity. Now just to review, for linear equations like let's say y is equal to 2x plus 3, I'm just going to draw a rough sketch. So it starts at 3 with a slope of 2. Let's say it looks like this. The domain for a linear function is just negative infinity to infinity. The range is the same thing. Now the next one that we considered was a quadratic function. Let's say if you have 3 plus x squared. The graph is going to start at 3 and it's going to open upward. It's been shifted 3 units up. So the domain for any quadratic function, x can be anything. It's always going to be negative infinity to infinity. However, the range will change. Notice that the lowest y value is 3, but it goes up to infinity. So the range is from 3 to infinity. Now if you have a downward parabola, let's say like y is equal to 5 minus x squared. Your graph is going to start at 5 and it's going to open downward. It's been shifted up 5 units. So your domain for any quadratic function where you have x squared as your highest degree, it's always going to be negative infinity to infinity. The range though is from, let's see, your lowest y value is negative infinity because these arrows will go all the way down. Your highest y value is at 5. So from low to high, negative infinity to 5. It stops at 5. So for your domain, you're looking at it from left to right. From the range, you're looking at it from low to high, or bottom to top. Now the next thing that we considered was an absolute value function. So let's say if you have 2x minus 3 plus 1. So the graph shifts 3 units to the right, up 1, it starts here, and the slope is 2. So I'm just going to draw a rough sketch. Your domain for any absolute value functions is negative infinity to infinity, unless you have like a piecewise function. Your range, notice that your lowest y value is 1, but it goes up to infinity. So it's from 1 to infinity. And let's say if it opens downward. Let's say you have 3 minus absolute value of x plus 2. So it shifts 2 units to the left, and it's shifted up 3 units, so it starts here, but there's a negative in front of the absolute value, so it goes like this. It goes downward with a slope of 1. So your domain is everything for this function as well, but the range, the highest value is 3, the lowest value is negative infinity. So it starts from low to high, negative infinity, and it stops at 3. Now for cubic functions, let's say if we have x minus 1 cubed plus 2. As you move 1 to the right, it's going to be shifted up 2. And there's no number in front of here, so it's just a 1. And because it's positive, it's going to be increasing rather than decreasing. So it's going to look something like this. For this type of function, your domain is also everything. There's no restrictions on x. Your range is also everything as well. It goes down to negative infinity and up to infinity. So for any cubic function, domain and range is just our real numbers. So now let's go back to radical functions. Let's look at our next example. Let's say if we have the square root of 5 minus 2 minus x. So the first thing we want to plot is the first point. So if you set the inside equal to 0, 2 minus x is equal to 0, you're going to get x is equal to 2. So it shifts 2 units to the right, and it shifts up 5 units. So it starts somewhere here. The question is, what direction is it going to go? Is it going to go towards quadrant 1, towards quadrant 2, towards quadrant 3, or towards quadrant 4? Because knowing the direction is important, because we need that if we don't want to make a table. So notice that we have a negative in front of the radical and a negative in front of x. Do you see that? So x is negative and y is negative. X and y are negative in what quadrant? Has to be quadrant 3. So it's going to be going in this general direction. So now, we don't have a number in front of the radical. So we can use our general transformation. The square root of 1 is 1. The square root of 4 is 2. And the square root of 9 is 3. So as we go 1 unit to the left, it's going to go down 1. And as this is x, this is y. So as we travel 4 units to the left, it's going to go down 2. So it's going to be over here. And as we travel 9 units to the left, starting from this point, it's going to go down 3, so it's going to be over here. Now for this, if you prefer, you can always make a table. So I'm going to do one example by making a table so you can see which points to choose. And there's the graph right there. So let's say if you have y is equal to the square root of x plus 1 minus 3. And you want to make a table. The first point you want to plug in is negative 1. And it's going to be negative 3. Because that's a shift. It shifts 1 to the left and down 3. Now, from that point, let me just put this number here. You want to go 1 to the right. So let's plug in 0. If you plug in 0 for x, the square root of 1 is 1, and 1 minus 3 is negative 2. Now your next point, you don't want to plug in 1, 2, 3, and 4. You want to plug in numbers that are perfect squares, because you can square root it. The reason why I plug in 0 is because I can square root 1. The next number I'm going to choose is 3, because 3 plus 1 is 4, and the square root of 4 is 2. 2 minus 3 is negative 1. Now the next point I'm going to plug in is 8, because 8 plus 1 is 9, the square root of 9 is 3, and 3 minus 3 is 0. If I want another point, I'm going to plug in 15, because 15 plus 1 is a perfect square, 16. The square root of 16 is 4, 4 minus 3 is 1. So you want to plug in numbers that are perfect squares, where the radical would simplify to an integer, and that's going to make your life easier. And basically, the way I was plotting points for these other functions is based on this pattern of numbers. So let me show you. So we know it shifts 1 to the left, down 3. So this point is this one, negative 1, negative 3. And for radical x, radical 1 is 1. So as we move 1 to the right, it's going to go up 1. Notice that we have the point 0, negative 2. And the square root of 4 is 2. So starting from this point, if we move 4 to the right, which will put us at 3, it's going to go up 2. So notice we have this point, 3, negative 1. And then the square root of 9 is 3. So as we go 3 to the right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, we're going to go up 3, so it's going to be over here, which is 8, 0. So notice this technique gives you the points without actually making a table. And if you can master this technique, you can graph equations at a very fast rate. So our graph looks like this. Now keep in mind, let's say if we put a 2 in front, everything is going to double. So instead of going, as you go 1 to the right, you're going to go up 2 instead of up 1. As you go 4 to the right, you're going to go, instead of up 2, you need to go up 4, which is somewhere over here. And as you go 9 to the right, instead of going up 3, you need to go up 6, which will be somewhere over here. So your graph will look something like this. If it was y equals 2 square root x plus 1 minus 3. So the amount that you increase in your y values, just double it, that's it. If there's a 2 in front. If there's a 3, just triple it. So like if we use this pattern here, let's say if there was a 2, it would be 2 square root of 1, which is 2. If we plug in a 4, it's going to be 4. If we plug in 9, it's going to be 6. Square root of 9 is 3, times 2 is 6. So these numbers, the amount that we increase the y values, will simply double. Okay, so now let's move on to a different type of radical. A radical with an odd root instead of an even root. The square root of x, what we considered was this one. There's an invisible 2 that you don't see. So if it's even, it looks like this. But when it's odd, it looks like this instead. So negative cube root of x is going to look like this. By the way, keep in mind, this is the same as cube root of negative x. So even if you reflect it across the x-axis or across the y-axis, it's going to be the same, because this graph is symmetrical about the origin. So there's only 2 ways you can graph cube root of x. This way if it's positive, or this way if there's at least one negative. If there's 2 negatives, they can cancel, and it's going to be the same as this one, if you have a negative on the inside and on the outside. But now that we know what the parent function looks like, let's try some problems. So let's say if we want to graph the cube root of x plus 1 plus 2. So first you want to find out where the graph begins. So it shifts 1 to the left and up 2, so it's over here. Now let's look at our pattern of numbers that we're going to use to plot this equation. So the cube root of 1 is 1. So as you move 1 to the right, it's going to go up 1. And the cube root of 8 is 2. So as we move 8 to the right, it's going to go up 2. So 1 to the right, up 1. 1 to the left, down 1. Because we know the general shape is like this. It's increasing. Now as we go 8 to the right, so starting from -1, we're going to stop at 7. It's going to be up 2, so it's going to be over here somewhere. And as we go 8 to the left, it's going to take us to -9. So it's going to go down 2, so it's going to be over here somewhere. And so now we can just plot it. So it looks something like that. So that's how you can graph cube root functions. Now let's say if you have 1 over x. The parent function for 1 over x looks like this. And if you have -1 over x, it looks like this. It reflects over the y or the x-axis. Doesn't matter, it'll be the same. So let's try some problems. Let's say if we wish to graph 1 over x minus 2. So we have the general shape, but you want to plot the vertical asymptote. The vertical asymptote is when the denominator is equal to 0. So if you set the bottom equal to 0, you get x equals 2. That's the VA, the vertical asymptote. Now there's also a horizontal asymptote, which is y equals 0, which is over here. Whenever the degree of the denominator is greater than the degree of the numerator, the horizontal asymptote is at y equals 0. Now if you want to get points for this graph, there's really only one point you need. But let's make a table. I would plug in 3 for x because 3 minus 2 is 1, and 1 over 1 is 1. So at 3, it should be at 1. The next point I would plug in would be something to the left of 2. Let's say like 1. If you plug in 1, you're going to get -1. So it should be somewhere over here. So then our graph, it starts from the asymptote, and then it connects to this point, and then it follows the horizontal asymptote. So it looks something like that. You can add more points if you want. And this graph looks like that. So that's how to graph 1 over x minus 2. So let's say if we have y is equal to 1 over x plus 3 plus 4. The vertical asymptote is at x equals -3, based on this term here, if you set equal to 0. Now the horizontal asymptote for this fraction is 0 because it's bottom heavy. The degree of the denominator is higher than that of the numerator. But it's 0 plus this number, 4. So it's actually y equals 4. It's been shifted up 4 units. So let's make our graph. So the vertical asymptote is at -3. And the horizontal asymptote is at 4. And let's plug in some points. So I'm going to plug in 1 point to the right of -3. So that's going to be -2. And 1 point to the left of -3. That's -4. If I plug in -2, -2 plus 3 is 1. 1 over 1 is 1. If I plug in -4, -4 plus 3 is -1. And so I got those points. So -4, -1, it's around here. And -2, you know what? I forgot to add 4 to each number. So the y value should be 3. And the y value here should be 5. Can't forget this 4. But I plotted at the right point for some reason. At -2, it should be at 5. So somewhere over here. Now we can make our graph. So this one's going to look something like this, and this graph is going to look something like that. As you can see, it's been shifted left 3, up 4. Now let's say if we have a negative value. Let's say y is equal to negative 1 over x minus 1 plus 2. So the vertical asymptote, if you set x minus 1 equal to 0, x is equal to 1. The horizontal asymptote is going to be y equals 2, based on this number. So here's the horizontal asymptote, and the vertical asymptote is at 1. Now notice that we have a negative sign, so instead of the graph looking like this, it's going to be like this instead. So let's plug in points. Let's make a table. So I'm going to plug in 2 for x and 0 for x. 2 minus 1 is 1, but times negative 1 divided by 1 is negative 1 plus 2, so that's 1. If we plug in 0, it's going to be negative 1 over negative 1 plus 2, and we're going to get 3 if we plug in 0 for x. So we have the point 2 comma 1, which is over here, and 0 comma 3, which is here. And so this graph is going to look like this, and this one is going to look like that. So now you know how to graph parent functions, 1 over x functions. Now let's say if you have 1 over x squared. It's very similar to 1 over x, but both curves are above the x-axis. If you have negative 1 over x squared, it's going to be below the x-axis. It's going to look like this. So this graph is symmetrical about the y-axis. The other one, 1 over x, was symmetric around the origin. So let's try one example. Let's say if we have negative 1 over x minus 2 squared plus 3. The vertical asymptote, you set the bottom equal to 0, you're going to get x equals 2. The horizontal asymptote, it's simply y equals 3. So for these types of rational functions, always plot the asymptotes first. So let's make a table. I'm going to plug in 1 for x and 3. 1 unit to the left and 1 unit to the right. So if I plug in 3, 3 minus 2 is 1, 1 squared is 1. Negative 1 over 1 is negative 1 plus 3, that's 2. If I plug in 1, 1 minus 2 is negative 1, but if you square it, it becomes positive 1. Negative 1 over 1 is negative 1 plus 3 is 2. Notice that they have the same y value, which means they're symmetric around about the y-axis, but in this case, it's going to be symmetric about the vertical asymptote because it's been shifted 2 units to the right. So if we plot 1, 2, that's over here. I mean, that's 3 comma 2, not 1, 2. 1, 2 is over here. But we can see the symmetry around the vertical asymptote. So it looks like that. So let's go over some different types of rational functions. Let's say if you have x squared plus 5x plus 6 divided by x squared plus x minus 2. Now, this function might seem complicated, but it's not really. We've pretty much covered this material. What you should do is you should factor everything. So to factor x squared plus 5x plus 6, think of two numbers that multiply to 6, but add to the middle term 5. 2 times 3 is 6, 2 plus 3 is 5, so it's going to be x plus 2 times x plus 3. To factor this one, look for two numbers that multiply to negative 2 but add to 1. So that's positive 2 and negative 1. 2 plus negative 1 is 1. So it's x plus 2, x minus 1. Notice that the x plus 2's cancel. So if you set x plus 2 equal to 0, x equals negative 2 is a whole. The vertical asymptote is based on this one, because the x minus 1 couldn't be canceled. So x equals 1 is the vertical asymptote. Now you might be wondering, what is the horizontal asymptote? Now, notice that the degree of the denominator is 2, and the degree of the numerator is 2 as well. When it was bottom heavy, when the degree of the denominator was higher than that of the numerator, like 1 over x, or 1 over x squared, the horizontal asymptote was y equals 0, plus if there was a constant here. If it was plus 3, then add 3. But we don't have that 3 there. So whenever the degree is the same, divide the coefficients. 1 divided by 1 is 1. So the horizontal asymptote is y equals 1 for this problem. So now let's graph it. So first let's plot the vertical asymptote at 1. Next, let's plot the horizontal asymptote at 1. So now at this point, we know the graph is going to look like 1 over x. It's going to be very similar to it. So we just need a few points. One point I would plug in is the whole, negative 2, because that's important. If we plug in negative 2, we just need to plug it into the surviving equation. So it's negative 2 plus 3, negative 2 minus 1. Negative 2 plus 3 is 1, and negative 2 minus 3 is negative 3. So we get the point negative 1/3. I would also plug in one number to the right of the vertical asymptote, as we did before, like 2. Let's see if I can fit it here. 2 plus 3 is 5, and 2 minus 1 is 1, so we just get 5. And plug in one number to the left of it. So let's say 0. 0 plus 3 is 3, and 0 minus 1 is negative 1, so we get negative 3. So negative 2 comma negative 1/3 is somewhere over here. And 2 comma 5 is up here somewhere. And 0, negative 3 is down here. So we can see how this graph is going to look like. It starts from one asymptote, it connects to these points, and it follows the other one. However, we did say this is a hole. So this should be an open circle. I know I drew a closed circle, but ignore the yellow point. It should be a hole there. Now for the other one, we know what the general shape is going to be. It's going to look something like this. You can add more points if you want, but that's a rough sketch of the graph. So let's try another function. Let's say if we have y equals x squared plus, let's make that 8x squared, divided by 4 minus 2x squared plus 1. So let's take out a 2 from the bottom. Notice that it's going to be 2 minus x squared. And we're going to set that part equal to 0. And we're going to solve for x. So x is equal to plus or minus radical 2. So we have two vertical asymptotes in this problem. Now to find the horizontal asymptote, notice that the degree of the numerator, which is x squared, is the same as that of the denominator. So what we're going to do is divide the coefficients. 8 divided by negative 2. So the horizontal asymptote is at negative 4, but we have a constant in front, so shift it up 1. So negative 4 plus 1, so it's at negative 3. So now we have the vertical asymptote and the horizontal asymptote. The square root of 2 is about 1.4. So the vertical asymptote is somewhere between 1 and 2. And we have another one at negative 1.4. And the horizontal asymptote is at negative 3. Now we know how the graph is going to look like on the right side and the left side. It can be like this. Or it can be like that. It can be like this. Or it can be like this. In the middle, a lot of things could happen. You can get something like this. You may get a curve that looks like this. Or sometimes it can even cross the horizontal asymptote. So for the middle, we got to plug in points to find out what's going to happen. So let's make our table. For this one, I would definitely use a table. Let's plug in 1 point to the left of radical 2. So let's plug in positive 2 for x. So that's going to be 6, well, 2 squared is 4. 8 times 4 is 32. And let's see, on the bottom we have 4 minus 2 times 2 squared. So that's like 4 minus 8, which is negative 4. And so we should get negative 8. So 2 comma negative 8. So it's like all the way over here. All we need is 1 point in this region. So we know the graph looks something like this in this area. So let's plug in another point. Let's say like negative 2. And notice that it's squared. So regardless if you plug in 2 or negative 2, the y value is going to be the same. So because it's both squared, it's going to be symmetric or symmetrical. So at negative 2, it's going to be like negative 8 again. So this is going to be the same. So the fact that it's symmetrical means that we're probably going to have something like this or something like this. So let's plug in 0 first. If we plug in 0 for x, everything is 0. So it's over here. Let's say if we plug in 1. 1 and negative 1 is going to be the same. If we plug in 1, it's going to be 8 over 4 minus 2. So that's 8 over 2, which is 4. So that's like over here somewhere. So we can see what's happening. This graph is going to look something like this at the center. So between two vertical asymptotes, you can't be certain what's going to happen, but if you see that both of these terms are even, like it has an even exponent, you know that there's going to be some sort of symmetry. It can be like this, or it can be like that. If it was odd, it could be like this at the center between the two vertical asymptotes, or it could be like that. You just got to plug in points to find out for sure. So that's it for that particular function. Now there's one more thing we got to mention, and that's rational functions involving a slant or an oblique asymptote. So notice that the degree of the numerator, which is 2, is greater than the degree of the denominator, which is 1. When the numerator is 1 degree higher than the denominator, you're going to have a slant asymptote. Now, what we should do first is we should factor everything before we begin. If we multiply these two numbers, 2 times 5 is 10, and two numbers that multiply to positive 10 but add to negative 3, doesn't happen. It doesn't work, because 2 times 5 will add up to 7, negative 2 and negative 5 will add up to negative 7. So we can't factor the numerator. If we could, we should. We know the vertical asymptote is going to be x equals 2. Now, whenever the numerator is higher than the denominator, there's no horizontal asymptotes, but we do have a slant. So we need to do long division to find a slant asymptote, but we don't have to complete the entire long division process. there's a certain point where we can stop, where it would suffice and we can have the answer. 2x squared divided by x is 2x. After you divide, multiply. 2x times x is 2x squared, and 2x times negative 2 is negative 4x. So let's subtract. So here we get 0, negative 3x minus negative 4x, which is like plus 4x. You get x, and bring down to 5. X divided by x is 1. Once you get this constant here, that 1, you can stop. So the slant asymptote is 2x plus 1. So now we can graph it. So at 2 we have the vertical asymptote. And to plot the slant asymptote, notice that we have a linear equation in slope-intercept form, which we covered at the beginning of this video. So we're going to plot the y-intercept, which is 1. And the slope is 2 because there's a 2 in front of x. Excuse me. So as we move 1 to the right, go up 2. And as we move 1 to the right, go up 2 as well. And then we're going to plot it with a dashed line. Now, these two asymptotes separate the graph into 4 regions. So we can have a graph that looks like this. It can look like that. It can be over here. Or it could be here. It's going to be in 2 out of those 4 regions. And the only way to find out which region it's going to be is to plug in points. We only really need to plug in 2 points. 1 point to the right of the vertical asymptote and 1 point to the left. So let's say if we plug in 3 for x. 2 times 3 squared. 3 squared is 9 times 2 is 18. Negative 3 times 3 is negative 9 plus 5. So that's 9 plus 5. That's 14 on top. 3 minus 2 is 1. So we get 14. So at 3, it's clearly above it's way above the slant asymptote. It's all the way at 14, which our graph doesn't go that high. So we're going to say it's in this region somewhere. We don't have enough space to plot it. Usually, if it's in that region, then chances are it's going to be in this region. But let's find out for sure. So let's plug in a number less than 2. Let's plug in 1. So 2 times 1 squared is 2, minus 3 times 1, which is 3, plus 5, over 1 minus 2. So that's negative 1 plus 5. That's 4 over negative 1, so it's negative 4. So at 1, it's at negative 4, so it is in this region. Let's go ahead and plug in 0 too, because 0 is an easy number to plug in. It's going to be 5 over negative 2, which is like negative 2.5, just to make this graph a little bit more accurate. So our graph is going to look something like this. Now the more points you add, the more accurate your sketch will be, but it's up to you how many points you wish to add. But usually on a test, you might get a multiple choice question, and all you need is 1 point to the left and 1 point to the right of the vertical asymptote, and you could eliminate the wrong answers to get the right answer. Or you could just use the graph calculator. So now we're going to focus on graphing exponential equations. So let's say if we have y is equal to 2x plus 3 minus 1. Now, what you want to do is set the exponent equal to 2 numbers, 0 and 1. So if you solve for x, you get negative 3 and negative 2. These are the points that you should plug in into your x and y table, which I would recommend for this type of problem. So if you plug in negative 3 for x, negative 3 plus 3 is 0. 2 raised to 0 is 1. Anything raised to 0 power is 1. And then 1 minus 1 is 0. If you plug in negative 2 for x, negative 2 plus 3 is 1. And 2 to the 1 is 2. 2 minus 1 is 1. Now this number that you see here, this is the horizontal asymptote for an exponential function. So we're going to plot that. So we have it at negative 1. And there's no vertical asymptotes for exponential functions. Your next thing, after you plot the horizontal asymptote, plot your 2 points, negative 3, 0, and negative 2, 1. So the graph, it starts from the horizontal asymptote and it follows those 2 points. And that's how you can graph it. You can add more points if you want, but I think that sketch is good enough. So let's try another one. So let's say if we have y is equal to 2 minus 3 raised to the x plus 1. So set the exponent x plus 1 equal to 0 and 1. And solve for x. So x is equal to negative 1 and x is equal to 0. And then make your table. So we're going to plug in negative 1 and 0 for x. If we plug in negative 1 plus 1 is 0. And 3 to the 0 is 1. 2 minus 1 is 1. If we plug in 0, 0 plus 1 is 1. 3 to the 1 is 3. So we have 2 minus 3, which is negative 1. This number is the horizontal asymptote. It's the number, it's the constant that doesn't have an x. So the horizontal asymptote this time is at 2. And if we plot our points, negative 1 comma 1 and 0 negative 1. So start from the horizontal asymptote and connect the 2 points. So that's how you can graph that particular exponential equation. So the last thing we're going to look at is graphing logarithmic equations. So let's say if you have log base 2 x plus 1 minus 3. So exponential functions are they're like the opposite of logarithmic functions. Exponential functions have horizontal asymptotes. Logarithmic functions have vertical asymptotes. Now what you want to do is you want to set the inside part of the log function equal to 3 things rather than 2 things. Set it equal to 0, which will give you the vertical asymptote. Always set it equal to 1, and set it equal to whatever this number is, the base. So the first one, we get x is equal to negative 1. That's the vertical asymptote. The next point, we get 0, and here we get 1. So let's make our table with these 2 points, 0 and 1. If you plug in 0 for x, you get 0 plus 1. Log of 1, regardless of what the base is always 0. So you have 0 minus 3 is negative 3. If we plug in 1, 1 plus 1 is 2. So we have log base 2 of 2. The 2's cancel and give you 1. And 1 minus 3 is negative 2. So that's why I chose those numbers, because you get nice whole number integers to deal with, which makes it easier to graph. So the first thing you want to do is plot the vertical asymptote, which is at negative 1. And then plug in your points. So we have our first point at 0, negative 3, which is over here, and then 1, negative 2. So start from the vertical asymptote and then follow the 2 points, and that's how you graph it. Let's try our final example. So let's say y is equal to 2 minus log base 3 x minus 1. So set the inside equal to 0, 1, and the base, in this case, which is 3. So the vertical asymptote is x is equal to 1, and our other points are 2 and 4. So let's make our table. So if we plug in 2 for x, it's 2 minus 1, which is 1. Log of 1 is 0, so 2 minus 0 is 2. If we plug in 4, 4 minus 1 is 3. Log base 3 of 3 is 1. And so 2 minus 1 is 1. So our vertical asymptote is at 1. And we have the point 2 comma 2, which is over here. And the next one is 4 comma 1. So the graph has to start this way if it's going to connect to those 2 points. And that's how you plot it. So that's it for this video. Now you know how to graph almost any equation. There's other equations too, but for the most part, we covered the most common equations that you'll see throughout your algebra, trigonometry, pre-calculus, and calculus course. So if you see any new equations that you have to graph, you can apply the principles that you've learned in this video to those equations as well. So that's it, and thanks for watching this video, and have a great day.